Efficient design for fixed-width adder tree using carry select adder. Abstract adder tree is the design of the adders in the parallel way. The conventional, ED, have full-width adder tree and fixed-width adder tree types. In the existing method, input vectors are truncated for the effective design of the fixed-width tree to get the output more accurately. The ripple carry adder, RCA, is used in the design of adder tree. The proposed design fixed-width adder tree is more effective than the traditional designs, and calculates the output almost with the same accuracy as the post-truncated fixed-width and of fixed-width ED. This paper mainly deals with the replacing of adders to reduce the delay, as adder tree is conventionally proposed with ripple carry adder. Hence in this paper RCA is replaced with carry select adder, CSA, to lower the critical path delay to fasten the hardware system of adder tree and efficient design of adder tree with CSA suggested. Introduction. Mobile devices and DSP hardware requires low power, area, efficient designs for better performances. Fixed-point VLSI systems have digital signal processing, DSP, algorithms to be implemented. These designs require adder tree, ED, which are commonly used in parallel designs. The shape of adder tree is different from SAT. Consequently, word length grows in a different order in SAT and ED. Multiplier deals with partial products. Hence, we prefer adder trees to get complex design easy. But the fixed-width adder tree and multiplier are not appropriate when we compared regarding schemes. Since, the fixed-width ED produces different shaped matrices compared to the fixed-width multiplier. However, direct truncation and post-truncation methods are employed to the FX-AT and FL-AT conventionally. In direct truncation, DT, one lower order bit of each adder output of full-width adder tree is post-truncated, and in case of post-truncation final adder output of FL-AT lower adder bits are truncated. However, these adder trees are implemented using ripple carry adder to get accurate results. It is necessary to have a different approach for developing efficient FX-AT design, which is currently missing in the literature. An efficient FX-AT design certainly helped to improve the efficiency of dedicated VLSI systems implementing complex DSP algorithm. Carry select adder contains multiplexers and adders. Giving source voltage and ground to the 2-bit adders saves time separately. And the selection line for all the multiplexers is the only one resulted carry which decides the other carry input. And this operation of the carry select adder leads to the lower delay in the hardware. Hence, to achieve the lower delay, RCA in the adder trees are replaced with carry select adder, as it is the main idea of the proposed paper. However, the area that occupied is more when we compared to the RCA. This area is reduced by lowering hardware measurement, and the time delay when we compare RCA to CSA in adder tree. It means the delay got increased from adder to get the reasonable delay shrink to get the same accurate output. Hence, we suggest carry select adder to get into the adder tree. Adders like carry look etc. also gives lower delay, but they occupy higher area which gives little area than CSA at hardware design. Hence, when compared to our proposed adder trees, CSA gives lower delay besides little ascent area when compared to RCA. The design like fixed width, FX-AT, full width, FL-AT, are truncated to get the output more rapidly. However, we are adding compensative input to the truncated adder trees. Hence, bias estimated formula is required to replace neglected input to the adder, which result in approximate adder adding in the design. Direct truncation and post-truncation process does not give efficient design of adder tree. Hence, approximate adder are introduced conventionally for replacing lower significant bits. The main contribution of this paper is 1. Designing of proposed adder trees by replacing RCA with CSA and lowering critical path delay, CPD. 2. Suggesting better adder tree to get the efficient output with lower CPD. Arrangement of input bits in matrix form. Truncation is understandable by arranging the bits in the matrix form. Bits of the vector are arranged in the column-wise in the matrix. These arrangement gives understandable adder tree easily, and they are arranged and divided into two parts, MSP and LSP. The calculation of MSP and LSP is discussed further. The truncated input columns are calculated consecutively to get the resulted output with adder inside, at which the ED plays the prominent role in the CPD. Hence, to calculate this adder is designed in CSA at adder calculation. Let the bit matrix be A for n equals 8 and W equals 8, 8*8, matrix is taken as example for 8-bit. However, for the truncated input, neglecting or removing LSP and calculating the MSP gives the calculation more easier than a full-width adder tree and FX-AT. Earlier, the adder trees are executed with RCA. And the delay having in ED is reduced by using CSA, which is proposed in this paper. A equals full-width adder tree, FL-AT, and fixed-width adder tree, FX-AT. A scheme to develop an efficient FX-AT design with truncated input. Use of truncated input in FXAT offers two-fold advantages. 1. Area and delay saving within the FXAT due to reduction in adder width, by p bits, and 2. Creates a scope to optimize other computing blocks appear at the upstream of it in a complex design. However, the use of truncated input introduces a large amount of error in the FXAT output which needs to be biased appropriately. Truncated fixed width adder tree, TFXAT. Full width adder tree and fixed width adder tree are truncated to get the efficient design and to reduce the CPD mainly. For truncation we need to know how many columns in the matrix are to be truncated. To achieve that we are going to know the estimate the fixed bias by using probabilistic approach. According the formula we are eliminating last three columns are chosen as the LSP. For proposed truncated fixed width adder tree we are calculating MSP and adding estimated input to the adder tree by using following formula. Output of TFXAT is expressed as y equals MSP plus 2PS. S equals n/2. The fixed bias for n equals 8 and 16 is found to be S equals 4 and 8. The input bit matrix of TFXAT with fixed bias is shown in Fig. 3, A, for n equals 8 and W equals 8. The binary values of S equals 4 is added to the least significant column of MSP for error compensation. It can be seen in following figure. As when the above picture is observed 5-bit is taken as input and for the error compensation we get LSP n equals 3, hence we are removing LSP and adding remaining bits in adder tree with the required adder. Improved truncated fixed width adder tree, ITFXAT. In ITFXAT we are adding half adders and modified half adder which gets the estimated formula to calculate it more efficiently. However, it also have estimation formula for MSP. The better efficient it is ITFXAT when compared to other adder trees. They are designed according to the usage of RCA. But to improve the fast response RCA is replaced with CSA. When CSA is used with other half adder and modified adder delay become more. Half adder is represented as A and modified half adder is as A star. And the adder tree is represented as below. Here in ITFXAT the carry bits which are added to the MSP is taken from the part of the LSP. Here LSP is divided into MJP, major part, and MNP, minor part, and MJP is added to MSP. To get the approximate result, S equals major plus minor. As the MSP requires the bias, MJP needs half adder and modified adder to get the approximate adder. MJP is gone through required half adder and modified half adder further to get the better output. Design of the different types of adders using DSCH2. Here we are using DSCH2 and micro-in software technologies to get the critical path delay. As DSCH2 has symbolizing method to get the complexity in design easier. By this we can execute it in Verilog 2. And we can get the waveforms in micro-in technology and other parameters. The result is got for 8,1632 bits gives the increasing CPD by increasing bits as input. By increasing number of bits there is high difference between critical path delay between CSA and RCA. And as coming to the efficiency TFXAT is better than ITFXAT to get the output. Hence TFXAT is better than ITFXAT in critical path delay. To know which tree is efficient as well as with lower CPD designing of adder are done to get output and DCDA and DSCH2 is done. In designing of adder trees there will be problem in designing in backend. Hence to reduce the design complexity DSCH2 provides symbolizing procedure. By that we can design the adders easily. Symbolizing. Fig 5.1 a 8-bit adder using symbolized 4-bit adder. Fig 5.1 b symbolized 8-bit adder. As the above figures are observed there the 8-bit adder turns into symbolized by this calculation. ODCDA is also easy. Different types of adder trees using DSCH2 by replacing RCA using CSA. By observing the above picture repulsing of RCA with CSA is noticed at the adder tree and by this we calculate the CPD separately and difference in the CPD is observed. Likewise below pictures are designed with CSA to calculate CPD. Suggested adder tree. In truncated adder tree, improved truncated fixed width adder tree is easy to design and get output more easily. However, we are adding half adder and modified adder tree to the improved FXAT. Those adders slow down the speed of getting output when CSA is used. Hence, truncated fixed width adder tree to get low delay. Hardware time complexities. As the CSA has extra muxes and adders the area occupied at the hardware is little more than RCA. By following novel techniques and linear DSP algorithms and transforms by using advanced technologies like 40nm we can reduce the area of CSA at hardware. By the above pictures we observed the DANE of ITFXAT and TFXAT are done and CDA is calculate. To calculate which adder tree is better to get low CDA different types of adder trees are simulated. Hardware time complexities. As the CSA has extra muxes and adders, the area occupied at the hardware is little more than RCA. By following novel techniques and linear DSP algorithms and transforms by using advanced technologies like 40nm, we can reduce the area of CSA at hardware. As the hardware technology can determined in microwind tool. However, it may extended to the hardware to reduce the area by applying different type of algorithms. Microwind unifies schematic entry, pattern-based simulator, spice extraction of schematic, Verilog extractor, layout compilation, on layout mixed signal circuit simulation, cross-sectional and 3D viewer, netlist extraction, BSIM4 tutorial on MOS devices and sign-off correlation to deliver unmatched design performance and productivity. In the future technologies we can reduce the size of the hardware and get the approximate result and with the same CDP. Hardware. These leads to the design of hardware specimen in VLSI design technology. And the output is also observed in the microwind. Applications. Multi-functioning of electronic devices. The best application of the adder tree. Application of passwords, security patches, encrypted languages, etc. In electronic devices like mobiles, laptops, we do multitasks with less amount of delay. Interpreters, compilers, applications. Image recognition applications like sharpening images, editing images via adder trees. Calculating barcodes, QR codes, etc. However, in TFX error compensation, fixed bias leads to reconstruction of image via what transform and sharpens the image with low time delay. We have estimated CPD of all the designs, and the estimated values are also listed. For word length, 8, 12, 16, the proposed ITFX offers 37%, 23%, 22%, and 51%, 30%, 27%. ADP saving over the FX at PT for N equals 8 and 16, respectively, and calculate outputs with almost the same accuracy of FX at PT and TFX at has better result when we compared to the other when the results are seen it on table. Conclusion. In this paper, RCA is replaced with CSA in ED to get lower CPD. As adder tree deals mainly the area and delay in getting the output. Hence, we undergone different types of truncated adder tree. Based on the proposed scheme, truncated adder tree. Based on the proposed scheme, truncated fixed width adder tree is the best possible way to get the output with the least delay.